The first method we are going to apply for feature extraction from this data set is based on Fourier transform, and for that purpose we are going to examine application of FFT or fast Fourier transform in Python. This figure is showing a principle of a decomposition of signal into periodical components. Fourier showed that any periodic signal can be written as a sum of sine waves with different amplitudes, frequencies, and phases. Left graph is showing time domain signal and on the right side is frequency domain signal. After we do this transformation with input time signal, the outputs are amplitudes and phases of the signal components in range from 0 to the half of the sampling frequency, and it's covered by n divided by 2 plus 1 points, where n is the number of time samples. In our case, we have 2000 samples in 1 second, and the outputs are 1001 amplitudes and phases for frequencies from 0 to 1000 Hz. First, we will import the same packages as in the previous tutorial, and the additional packages like additional set of colors for matplotlib and order_dict, which will be used to sort matrices. Data is imported in the same way as before and then converted into SI units as before. For the purpose of demonstration, we will take one cycle from the first sensor, which is microphone, and analyze it with the FFT. Cycle number 3000 is chosen randomly, but user can try some other sensor or some other cycle. We can see that we are working with time series, but we don't have time axis defined. Here we have information that we are working with 2000 samples in one cycle. Documentation about the data says that the sampling period is 1 second, and because of that we will create real-time indices of samples which we need for plotting in time domain. We used existing NumPy functions FFT, RFFT to obtain frequencies and amplitudes of signal components. To obtain frequency, it was necessary to input number of samples and sampling time step, and as the output we obtained one-dimensional array of frequencies. To obtain amplitudes, only one input parameter is required, and that is time series array. Output is again one-dimensional array, but this time the array of amplitudes and phases which correspond to frequencies. Amplitudes and phases are stored in complex numbers and can be calculated in a very simple manner. We will use only amplitudes here, and they are calculated by taking the absolute value of complex number. Outputs from this cell are showing exactly that. This whole process will be much clearer after we look at few graphs from this example. We created two plots. First one is raw signal in time domain, and second one is frequency spectrum after Fourier transform. When we look at this spectrum graph, it's obvious that some frequencies are more dominant than the others, like these three here. The dominant frequencies have higher amplitudes, and because of that it's possible to reconstruct the signal that will be almost as original using only a percentage of the most dominant frequencies. This is good in terms of data size reduction, which makes it easier to work with them. Here we define number n, which is the percentage of the most dominant frequencies we want to use, and it can be changed as desired. Now we will sort the frequency spectrum based on amplitudes. Convenient way to do this is to use dictionary, as we did. In dictionaries, we have the keys and we have the values. Our keys are frequencies and our values are amplitudes. With function order_dict, we sort the dictionary according to values. To reconstruct the signal, we will find the threshold amplitude and delete all amplitudes that are lower than the threshold. After selecting the most dominant part of spectrum, we will plot our selected spectrum along with the original one. Then we can have a look at the sorted spectrum to see the range of amplitudes of selected data. Labels for frequencies are not present here on this graph. And at the end, the most important part is the reconstruction of signal, for which we used inverse FFT. We see that basic trend and oscillations are captured very well. User can repeat this procedure for different sensors, for different EMC cycles, or for any other time signal.